Good morning, everyone. My name is John McLennan. It's my pleasure this morning to introduce a new seminar series. This is the Forge Geothermal webinar series, where we bring together industry leaders to describe some of their experiences and aspirations and predictions for enhanced geothermal systems. And as this is the inaugural seminar, I'm extremely pleased to introduce Jack Norbeck. Dr. Jack Norbeck is the founder and co-founder and chief technology officer of Fervo Energy. And at Fervo, he leads the exploration and production activities. He is a geothermal reservoir engineer with a focus on numerical reservoir simulation, geomechanics, and induced seismicity. Prior to Fervo Energy, Dr. Norbeck was a Mendenhall postdoctoral fellow at the U.S. Geological Survey. He holds a BS degree in civil engineering from University of Colorado, an MS degree in civil engineering from Colorado School of Mines, and a PhD degree in energy resource engineering from Stanford University. Jack was the president of the SPE student chapter at Stanford from 2014 to 2015. So ladies and gentlemen, it's my real pleasure to introduce Dr. Jack.
Thank you very much, John. Appreciate the introduction and really appreciate the opportunity here to kick off your new webinar series. As you mentioned, I'm co-founder and CTO at Fervo Energy. So I thought to kick this off, I just provide an introduction to some of the stuff that we're working on at Fervo, a little bit of the background and motivation for what we're doing, and also hopefully share a few updates on some of the projects that we're working on, both the kind of field scale demonstration projects that we have going on, as well as some of our R&D initiatives. So John, can you just confirm that you see my full slides here? Rogosha?
Yes, we do.
We do, okay.
And hopefully the attendees as well.
I hope so. Then we'll just jump into it. So as said, I'm just going to provide an introduction to Fervo and share some updates on some of the stuff that we're working on. So we really founded the company back in 2017 around the thesis that there had been so much technology innovation that had occurred in the oil and gas industry over the last 10 years, but we didn't see that technology transferring into geothermal. And we saw a way that leveraging some of these technologies, horizontal drilling and multi-stage stimulation, had a big opportunity to both open up new geologies, help make geothermal a little bit more scalable, but also make it significantly more cost effective. So if you look out there, what's the overall prize for geothermal? There's something on the order of at least 100 gigawatts of potential in the United States alone. That would be about 20% of United States energy supply, and it also represents something like a $300 billion market opportunity. If geothermal can be successfully deployed at the 100 gigawatt scale, then that also could have huge climate impacts and would offset something like half a gigaton of CO2 emissions per year, which is on the order of 1 or 2% of global emissions. So there's a huge prize out there. There's also a huge opportunity for geothermal to play a major role in supporting the broader energy transition and fighting climate change, in the sense that it provides 24/7 reliable energy. And so it works very well with other renewables. And in fact, the more geothermal we can bring onto the grid, the faster we can also ramp up solar and wind and other variable renewable energy sources without having some of the challenges that come along with that in terms of reliability. So we're taking an approach to geothermal reservoir engineering and reservoir management that relies on horizontal drilling, also multi-stage zonal isolation. We're also taking advantage of some of the more modern downhole diagnostic technologies, and in particular have a major focus on what we're doing with distributed fiber optic sensing to help monitor and characterize some of the downhole conditions in real time. So broadly speaking, I just have a couple of schematics here and we'll get into it in more detail as we go through the presentation, but we're looking at drilling horizontal wells down to depths to meet our target temperature window of about 175 to 225 C, and drilling out sequences of injection and production wellbores that we can use to effectively mine the heat out of the rock. So we take advantage of as I said, multi-stage zonal isolation, multi-stage stimulation approach. And you can see here just an example simulation result of essentially what we're talking about and forms the basis of our reservoir engineering design is making use of what's called plug and perf stimulation treatments. And this well you can see here in this synthetic example is a well that's been stimulated with 10 stages, 3 clusters per stage. So there's a total of 30 fractures that connect these wellbores and provide hydraulic communication. The fractures provide the heat transfer surface area, and they also provide the fluid flow pathways and injectivity and productivity that the system needs. So as I said, I'll get into a little bit more, but just wanted to present a high level overview of the type of design we're working with. So I also thought I would take the opportunity today in front of a wider audience to talk a little bit about some of the market trends that we're seeing as a private developer in the space. And it's truly, there's been a resurgence in geothermal, as many of y'all are aware of, and there's a number of factors driving that. And I'll touch on just a few of these, but one I want to make sure to hit on is here in the upper left where it says 1,000 megawatt under state and federal policy. So if you aren't aware, the California Public Utilities Commission back in 2021 issued a new law, and it was a result of some of the rolling blackouts that occurred in California in 2020. They did a lot of studies understanding, how are we going to improve grid reliability, but also meet our climate targets. And they found that geothermal is one of the only solutions that really solves both of those problems. And so they actually issued a ruling that utilities in California had to procure 1,000 new megawatts of geothermal power by 2026. And so this is, I don't think I'm understating it when I say this is probably the most important thing that's happened to the geothermal industry in the last decade, because this is now mandated and can't be reversed. And so if you think about the opportunity there for the industry, 1,000 megawatts represents something like 200 to 300 new wells that need to be drilled just in the next 5 or 6 years. So of course that's a tall order, but it's also a huge opportunity in terms of, driving drilling costs down the learning curve, getting more deployment out in the field, and so forth. So I really want to make sure that everybody's aware that this is a really special time for the industry, and the industry has to step up, and other policymakers and federal funding agencies need to recognize both the challenge and opportunity here. Of course, a lot of corporates are now looking at powering things like their data centers and other energy use and energy consumption with what's called 24/7 carbon-free energy. So really around the clock, hour by hour, location by location, powering their operations with clean energy. And when some of the biggest companies out there like Google and Microsoft look around and ask what technologies are out there that can do this, geothermal is one of just a handful of technologies that can, and they're very excited about that. It's also going to be, significantly more electricity demand in terms of converting more fossil fuel based energy sources to electricity, and also things like direct air capture, green hydrogen, EV charging. All of these really need, when you look into the economics, high capacity factor, round the clock clean power to be economic, and geothermal provides a good opportunity there. So there's a lot of exciting trends in the market that are driving customers to look at geothermal in ways that they haven't ever done before. And fortunately, Fervo is well poised to help capitalize on those market tailwinds. We've actually signed over 78 megawatts of new PPAs in 2021 and 2022 so far, and there's more to come. So we actually in May last year announced the first corporate agreement between a developer and a corporate for geothermal power. It's a 5 megawatt project with Google, and I'll touch on some of the updates to this project later in the talk. But this is a project that we're actively drilling and developing today in Nevada. We've also signed 2 greenfield power purchase agreements. These are both 15-year deals with community choice aggregate utilities in California, and are both responsive to that 1,000 megawatt mandate that I mentioned before. The first was with East Bay Community Energy, which is California's largest CCA. And we actually just announced this morning a new power purchase agreement with Clean Power Alliance, 15-year deal for the EBCE deal is 40 megawatts, CPA deal is 33 megawatts. That provides power to about 32 different communities in the LA area. So as I said, this is just, if you look at these two, 73 megawatts out of what's required in terms of 1,000 new megawatts, which is what the mandate is calling for. So you can expect to see more geothermal PPAs come down the pipeline as well. And, really fortunate to have great support both through federal funding, through grants, and also raising private capital with some of the leading venture investors out there. This slide just presents a little bit of our history in terms of fundraising, starting with just a $50,000 Tomcat grant from the Stanford Tomcat Center. We've since gone on to receive several $1 million of funding through the Geothermal Technologies Office, through ARPA-E, also through the Forge project itself. So very grateful to have the support of the Department of Energy in supporting our technology development. And then we've raised several rounds of venture, most recently $138 million round led by DCBC, with really strong participation from some of our existing investors. So we feel like we've really set up a solid partnership to support us to go out and execute on these ambitious development goals. So hopefully that provides a little bit of context on Fervo, some of the background and where we're at today, and some of what the future holds for the geothermal industry at large. And I'll transition now into sharing a little bit about how I think about reservoir engineering and understanding reservoir performance, and some of the motivations for why we see horizontal drilling, multi-stage stimulation approaches being such an effective way at developing geothermal resources. So I thought I would just start higher picture and just talk a little bit about the broad drivers. And it's probably not intuitive for folks that haven't really dived into detailed project economics and project finance. But when you put together a project model and you test different sensitivities on what are the biggest drivers on overall project economics, you can look at things like your drilling costs, of course, are the first thing that come to mind. Your power output per well, what are your OpEx costs, how many wells are you drilling, what price are you getting in terms of your PPA, and those all jump out. But of course, probably the largest driver, and I just presented a sensitivity analysis here of some of these different factors. The largest driver in overall project economics is cost of capital. Okay, so, and you can see that represented here, moving, cost of capital as a base case from 8% up or down to 10% or 6%. And you look at the relative swings versus all of these other parameters, cost of capital ends up having the biggest potential upside or biggest potential downside risk. And as a reservoir engineer, you might say, well, I can't do anything about that. I'm a reservoir engineer. All I can affect is our reservoir performance and our well spacing and our output per well. Or if you're a drilling engineer, you might say, well, all I can do is focus on reducing drilling costs. I may as well go home here and leave this to project finance people, or and leave it at that. But that's not really the story. I mean, at the end of the day, cost of capital is about risk and what investors view a given deal in terms of risk factors. And in geothermal, it all comes down to, the biggest thing about that is, unfortunately, the geothermal industry has a pretty bad credit score when all things are said and done, just because of past history. And you start digging into why is that? And it's, 40% of all wells, geothermal wells drilled worldwide, are dry holes. A lot of projects go over cost because they encounter a lot of shallow drilling hazards and lost circulation and take twice as long to drill their wells, things like that. And so when I look about, what's the biggest way to influence project economics, a lot of it comes down to consistency in results. And there's a number of reasons why horizontal drilling provides more consistency relative to the current base case, which is vertical well drilling, basically targeting fault zones. And, and so it's all about delivering consistent flow rate per well. We don't want any wells to be a dry hole. And you look at shale, that's basically what's happened. You had similar, primary production oil and gas, you had a lot of dry holes. Nowadays with shale, all wells produce something. And so that actually has a major role to play when investors are looking at project risk. Delivering consistent initial temperatures per well, you can find basins that have relatively consistent thermal gradients, consistent geology, then that makes targeting the right temperature horizons easier ahead of time and lower risk. Drilling multiple wells from a single pad, all know that in shale, multi-well pad drilling has become the norm. So you look at, especially in the early days, where the biggest gains to be had, it's fast drilling in the surface hole sections. So these shale wells that are getting drilled in 12 or 15 days, they're getting down to the reservoir in 2 or 3 days. And so there's a lot of opportunity, especially in the early days, for reducing drilling costs by just mitigating some of those shallow geohazards, drilling all your vertical sections, 100 feet apart from each other. And then I also think, a big driver for drilling horizontally is scalability. So accessing wider range of lithologies. We don't really need these sweet spot hydrothermal systems anymore. And again, improving your flow rate per well. There's always 2 factors that control your output per well, and it's temperature times flow rate. So really, Fervo's approach is all about focusing on improving flow rate per well and the consistency therein. So you started looking, there's been a lot of work done on horizontal or highly deviated geothermal wells for decades now. And so there's actually a lot of work to build upon. The theory for understanding flow and heat transfer in a horizontal well system has been around since at least the 70s, when Gringarten published this paper. He's looking at highly deviated wells connected by sets of parallel fractures. And he put a lot of work into understanding some of the major drivers and how you think about the thermal performance over the long-term production history of a given system. And I'll talk a little bit about that in a moment. But this is back in the 70s. So when you look at, if you dig into this paper, they really limited their analysis to a total of 10 fractures. And if you look at what they're doing in shale now with 15,000 foot laterals and, 50 or 75 stages, and each stage has, they're getting more and more towards extreme limited entry designs where they have 10 or more fractures per stage. You're talking about hundreds and hundreds of fractures per well. So when we started looking into the literature here for geothermal, very often this was the case, and even more recent studies were kind of limiting their analysis to 5 fractures or 10 fractures at most in a lot of ways. But you can see even just from this study that going from 1 fracture out to 10 fractures, depending on your fracture spacing, can have a big impact on your thermal decline and thermal performance. And I'll just take this one step further to really show some more of the motivation for this. This plot that he put together is really, it's like a set of type curves for thermal decline. And so the y-axis is basically temperature decline, although it's inverted. I typically like to flip this around, but it goes from like 0 thermal decline down at the bottom up to the point at which your reservoir or production fluid declines to equal your injection temperature. It takes some amount of time for that to happen as the thermal front moves through the reservoir. And then each one of these type curves is for a different effective fracture spacing, essentially. And so, it's interesting to look at how some of these fracture spacing curves kind of pull apart at these higher numbers. But if you actually look in practical terms at what a reasonable amount of thermal decline is for any given power plant, you're kind of 20% is about the most you'd want to design for. And so actually there's not a ton of difference between different fracture spacing cases. And so then it's all a question of, well, how do you slow your rate of decline down one of these curves? And so I've just pulled out this dimensionless time number that that Greengarten was able to parameterize. And what you see is that he also had a slightly different way of looking at it. So I put this in terms of things that we think about more commonly now in like a horizontal well stimulation treatment design. But it's total flow rate through the system. And then you have your total number of fractures and then your fracture height and fracture length. So these combined are like your fracture surface area. And all of these are to the squared power. And so what this tells you is that if you select a given fracture spacing, you really want to reduce this number so that it takes longer and longer for you to meet some given level of thermal decline. And the main point I want to pull out here is that fractures, your total flow rate's typically fixed, more or less, but the things that we have control over now is number of fractures and total fracture surface area. So that's how many stages, how many clusters per stage, what type of treatment volumes are you going to pump to influence bigger fracture surface area. And since it's a squared power, in doubling your total fracture surface area can reduce the time to thermal breakthrough by a factor of 4, or increase the time to thermal breakthrough by a factor of 4. So surface area and total number of fractures plays a huge role. And if there's one thing that the oil and gas industry has gotten really good at over the last decade, it's creating fracture surface area. So why not use some of those methods and apply them to geothermal? And by the way, this is basically similar for all geothermal systems that are dominated by flow through fractured reservoirs. The specifics are slightly different. The shape of these type curves might be slightly different, but it's all driven by surface area, but without taking a multi-stage stimulation approach, that becomes out of your control. You're basically relying on natural fracture surface area to get you there. Whereas we have the means, we have the technologies and the tools to do this already today. So more work has been done in the meantime. McClure and some of his students, when he was at UT, modernized the Greengarten model for more of a typical horizontal well design, and they found really promising results. And of course, nowadays we have access to much more state-of-the-art full physics reservoir modeling at our disposal. And so this type of reservoir modeling forms the basis of everything we do at Fervo. we're able now to use models that can model the full life of the field, both the drilling phase, the stimulation phase, and the long-term circulation phase, modeled in a single coherent simulation, with all of the right physics that are central to understanding the problem. So obviously fluid flow and heat transfer and fracture mechanics, but also looking at a detailed understanding of how multi-stage, multi-cluster completions work, offset well interactions, fracture initiation and propagation. We can put in, all of the latest and greatest in terms of fluid additives and fracturing fluid systems, so non-Newtonian fluid systems and proppant slurries, and understand how that impacts proppant placement. And then even some of the near wellbore processes that are really key to understanding injectivity and productivity of geothermal wells, but limited entry, perforation, pressure drop, fracture tortuosity, perforation, screen outs, all of these types of things are now all embedded in one consistent simulator. And we can model systems like this and then model out the thermal decline profiles over time. And so I'll just give a couple of examples of synthetic sensitivity study, just to give you all a sense of how performance looks like in some of these horizontal well systems. So I'm looking at just a doublet well system here, as you can see, just showing the discretization. I'm showing just 1 out of every 10 fractures in this. So there's actually hundreds of fractures that we're simulating along this reservoir. And one of the main outputs is looking at the thermal decline profile over time. And then you can start running sensitivity analyses on this. And I'll just give 2 examples here. This first one is, we're looking at a doublet system that's aimed to target about 5 megawatts of gross power. We're looking at different lateral lengths of 2,000 feet, 3,500 feet, 5,000 feet. So still on the lower range of what's possible in shale, but we've actually done this now, and so it's possible in geothermal to drill wells at least of this length. Looking at fracture spacing, how does that impact things? So we're looking at different cases of 25 feet, 50 feet, and 100-foot fracture spacing. So imagine that those lateral lengths cut up into many fractures spaced at constant spacing, and then we're looking at different cases of that. And we're looking at a constant circulation rate, in this case, of 1,250 gallons per minute. And the 2 curves are showing just net power and production temperature over time. And so what you can see is, for the cases where you have a shorter lateral length of 2,000 feet, you're getting steeper thermal decline, and then there is some impact of fracture spacing. If you're able to move out to 3,500 feet, you get into the realm where your decline is low enough to be manageable, and wouldn't impact your performance in terms of the power facility too much. And then longer lateral length, you're getting significantly lower thermal decline, but again, some impact of selecting the appropriate spacing. Fortunately, that's something that's under engineering control. Similar case, but here we're looking at different lateral lengths as we did before, holding fracture spacing constant and looking at how pumping different circulation flow rates through the system affects both thermal decline and net power. And there's some really interesting things here. Again, short lateral length at a high flow rate declines quite quickly. But if you can get up to 5,000 feet, you can actually put 50% more flow through the system without suffering too much thermal decline. And so this can have major impacts in terms of project economics, both the shape of this curve and how you're generating power over time in terms of time value of money, but also just total number of wells that are required to meet a given plant capacity. So we've spent years now modeling these different sensitivity cases and have found that for sure there is combinations of these engineering parameters like lateral length, frac spacing, treatment volumes, and so forth that get you into really solid project economics. I just touch on this really quick because I get asked a lot of questions about, well, what about thermal short circuiting, fast flow pathways? And again, a lot of the early studies that have looked at this found that it was very significant. They really looked at a small number of flowing pathways, like 5 or 10 total fractures, and said, well, what if one was really, really high perm? So we started looking into this. I specified the same system, but now instead of uniform fracture conductivity, looking at a log normal distribution of conductivity. Most fractures are really low conductivity, but a few fractures are really extremely high. So what does that look like? And absolutely, you get some, this is an odd angle showing from the bottom up, but it shows kind of where the cold, the formation's cooling down more quickly because it's taking more flow. And it certainly happens. It's a real phenomenon. But when you actually compare the overall thermal performance, at least in this case, it didn't have a significant impact. It was just by, over 20 years of it impacted things, maybe 10 degrees or so. So that's not to say this is a universal law. I think this is still a big issue that needs to be solved, and there needs to be a lot of R&D that goes into it. But I'll say, the larger number of fracture flow pathways has some ability to basically average that out. So I'll transition now and just share a couple of updates on some of the field scale demonstration projects that we are operating. And I'll give an example of a site out in Nevada. We began operating at this site in 2020. And our first major field project there was to do a full scale plug and perf multi-stage stimulation treatment. So we actually identified this site, partnered with an existing operator that's operating a commercial power facility there. It's currently underperforming, and so there's headroom for additional production. And so we went in there and recompleted an existing well. It was open hole slotted liner completion, so we recompleted it with a 4.5-inch casing, and we cemented permanent fiber optics behind casing in that well and performed just a 4-stage stimulation treatment. Not as many stages as you would expect to see in a full commercial project. And this project was never meant to be commercial, but it was really designed to target the technical validation and de-risking, also collect site-specific data on some of what we felt at the time were still some of the outstanding challenges and things that just hadn't been done in the geothermal industry before, like a multi-cluster stage with proppant. And so we were able to successfully recomplete that well and perform this 4-stage stimulation treatment. And at the time, it was the world's first multi-stage, multi-cluster plug and perf stimulation treatment in a geothermal field. And I'll just touch on some of the data here briefly. We were able to place industry standard proppant loading concentrations. We were able to show that the treating pressures were within our expected ranges, and didn't depend too much on lithology. We tested a range of lithologies, both metamorphic sediments and also more igneous intrusives, and found that the treating pressures and treating conditions were broadly similar across all different lithologies that we tested. Using the fiber, we were able to confirm that we did get breakdown at every perf cluster. And so we got good evidence of initiation at all clusters, again, irrespective of lithology. And we were also able to show that during the treatment, there was relatively good flow distribution as measured by the distributed acoustic sensing fiber. So Moving on, after successfully completing that project and collecting a lot of site-specific data, we built we built a plan to continue working at that same field and develop a 5 megawatt project. And we really kicked off the drilling campaign for this project earlier in 2022 in January, and has been hugely successful so far. We've this was the well that we did the testing in, what we call the proof of concept well. And following upon that, we drilled a 3-well drilling campaign that included a vertical monitoring well down to a little over 8,000 feet. And then we drilled a horizontal well here that's going to be used as the injection well for this doublet pair. And just more recently in September, we drilled and successfully cemented in place fiber optic cable along this horizontal production well. So there's a lot of, this took a lot of hard work from the Fervo team, along with a number of other partners, and has been thus far very successful. And in terms of drilling these types of highly deviated horizontal wells and geothermal rocks, a number of firsts. We had to, because it's a commercial project, these wells are designed with 7-inch production casing. And that's just something that along the lateral, and that's just something that's not standard in oil and gas. Almost all horizontal wells in oil and gas are completed 4.5-inch or 5.5-inch casing. And so this larger hole size required us to redesign the well, from that production section all the way up to have larger hole sizes. And so, this was the largest well diameter through the curve section in the onshore US that we're aware of, 14 3/4-inch hole through the curve. We achieved the highest build rates through the curve of any geothermal well. So we were meeting our target of 10 degrees per 100 feet of build rate through the curve. And of course, also drilled the largest well diameter in the horizontal section in onshore US, both geothermal or oil and gas, as far as we're aware. So we drilled both of these laterals with 9 7/8-inch open hole to fit our 7-inch casing plus fiber in both wells. You'll also notice something I'm very excited about for our producer well. We had a more complex curve trajectory. So we actually had a bit of back build and built a 3D curve to land at our target location for landing that lateral. So this is also proving very well that we can drill more complex well paths and drill multiple wells from the same pad, even in these harder metasedimentary and igneous rocks, and at higher temperatures, I should say. And here's just another example of what that system looks like in cross-section view. In July, we were able to complete a 16-stage hydraulic stimulation treatment in the injection well. This is now the largest multi-stage stimulation treatment in a geothermal formation. So it's 16 stages, 6 clusters per stage, a few more aggressive limited entry stages with 9 clusters per stage. And so there are over 100 discrete flowing pathways that we've created along this well at this point. All 16 stages were pumped successfully, close to as designed. We pumped about a little over 11 million gallons of slick water and 7.5 million pounds of proppant during this job. And a really strong focus on data acquisition. We had in-well fiber to look at temperature and DAS flow distributions. We had microseismic low frequency DAS in the offset well to measure strain signals. And we also had a very comprehensive induced seismicity monitoring program, including a local network and a traffic light system in place that we followed throughout this job. So very excited to share some of that progress on our field projects. There's more work to be done here. And we're excited to continue working on this project over the next several months. So I'm going to just follow on that and share one interesting example that came out of these field trials. And I think it has some really interesting lessons for the industry at large in terms of how we think about innovation in the geothermal industry. So what I'm going to be focusing on here is about performance of one of the key tools that's a part of a multi-stage plug and perf stimulation treatment design, which is the zonal isolation plug or the stimulation plug. You run one of these. How the process typically works, for those who aren't aware, is during each stage, you first run on a single wireline system this plug, and you set it, and then on the same wireline, you then go upstream of the plug and you perforate. That's hence the name plug and perf. So that reopens the formation, reopens the wellbore to the formation and establishes hydraulic communication through the perforations. And then when you're getting ready to pump your next stage, you drop a ball that flows down the well, seats somewhere here close to the seating element, and provides hydraulic isolation from everything downstream of the plug. And so all your fluid is forced into those perforations that are upstream. So that's a really key part of the treatment process. And there are questions about whether or not there were commercially existing plugs that would meet our temperature requirements in geothermal. And this is such a big issue. Actually, the GTO issued a funding opportunity back in 2018 to look into this. And we were fortunate enough to be awarded a $1.3 million grant to partner with Schlumberger to upgrade one of their existing product lines, both for higher temperature conditions, but also, and perhaps more importantly, upgrading it to larger casing sizes to meet our 7-inch OD casing. So this is just a picture of what this copperhead plug assembly looks like. It's got kind of aluminum housing fixture and a sealing element that expands when you set the plug. So we did a lot of work with Schlumberger. It took about 2 years to do R&D and testing and modeling and fabrication and more lab testing to verify that this plug would meet the standards that we set out to achieve. And here you can see an example of one of the test plugs that they developed with a new elastomer material. And ultimately, we were able to find an elastomer material that would meet our standards of 225 C or 450 Fahrenheit that would hold up for several hours, that a plug must be able to last for downhole. So very successful program overall, because this is a product that didn't exist previously and now is commercially available to the industry. So if you find that you do need these type of high temperature plugs, you can reach out and I can share some more details, but this exists now. So moving on, we're thinking, okay, well, let's think about this for our project. The horizontal wells that I showed you previously were completed in reservoir temperatures of about 370 Fahrenheit. And so we said, okay, well, for sure, that copperhead high temp plug that we just developed is going to meet that standard. But let's look out there across the market and see what else exists. And we found a composite plug line where they did have 7-inch ball drop flow through plugs they did have one even up to 375, but primarily their plugs maxed out at 300 degrees Fahrenheit. Okay, then we looked also at Schlumberger had a standard copperhead. We found that they did have a 7-inch line up to 35 pounds, and it was good to 350. Okay, so both of those are below our formation temperature. But let's think one step further about what are the conditions this plug's actually going to get exposed to. And so we did a lot of modeling trying to look into this, and kind of had the realization that obviously while you're pumping extremely high flow rates of 100 barrels a minute, 4,000 gallons a minute for many hours into a given stage, you're cooling down the wellbore quite a bit. And so we performed simulations of looking into this. We, background formation temperature was 400 degrees, treating rate was 100 barrels a minute. We pumped for 2 hours with 85-degree Fahrenheit fluid, kind of modeled what a worst case scenario might be, where, maybe you pump 2 stages successfully, but then while you're setting up for stage 3, you have some equipment malfunction or some operational challenge that requires you to kind of allow the worm to well back for 12 hours before you start pumping the next stage. So we looked at, used modeling to look into this. So here's just an example of treating pressure is this top curve, just kind of meant to show you when we're actively pumping. And then this curve down here is what's the actual wellbore temperature at the location of that next 3rd stage plug. So you can see while we're pumping, the well very quickly cools down to lower than 100 degrees. And then there is some warm back that happens fairly quickly, but it really only goes back up to 250 or so. And I think on the next slide, I have slightly more zoomed in, but yeah, so 3-hour shut-in phase, the temperature rebounded to 265. And then in the next stage, dropped again to 100. And then a 12-hour shut-in period, the wellbore only warmed back to 300 degrees. And so after doing a lot of modeling like this, we started saying, well, we can most likely get away with plugs that are rated to significantly lower temperatures, and quite frankly, are just cheaper and easier to mill out. So there's a lot of advantages for using these existing plugs. So get into the actual data and what we observed during this treatment. We ended up trialing 3 different plugs. We did 11 standard composite plugs, 4 standard copperhead, and then 1 of this EGS copperhead. We placed that in the final stage since it had never actually been run down hole before. We wanted to minimize our risk there. Now we had permanent distributed temperature sensing fiber optic cable behind casing to monitor temperature continuously throughout the entire lateral, throughout the entire job. And so we asked, okay, well, what was the actual temperature at our plug 16 location where this EGS plug was going to be sitting? And remember, the initial reservoir temperature was measured at 370 F. So then what I'm showing here is just on the top curve, just the treating plots for stages 15 and pump down between stages, and then the treating plot for stage 16 on the right. And then this is the curve that is showing the actual temperature measured in real time at that location where the next plug was going to be set for stage 16. You can see that during pumping of stage 15, quickly dropped to like 115 and then kept dropping down to below 100 degrees, very consistent with our modeling. And then after we shut in, for sure we saw some warm back, but it was limited to, we saw at that stage about 200 degrees. And this was, just to call your attention, a 12-hour, this is one of those worst case scenario issues where there was a 12-hour shut-in period that was caused by some operational problems we were having. So when we looked across the entire well, we saw that, especially these later stages, they get the cooling from all the previous stages. So they stay significantly below even our modeling was showing at 265. But when we looked at all stages, we did see a max of about 265 of warm back, which is very consistent with the modeling that we did. So I would say, in summary, this is one of those things that you really only start realizing when you really dig in, do the detailed engineering, modeling, and risk assessments to understand what are the true conditions and that downhole that these types of downhole equipment are going to be subjected to. And you may find that, you don't need to do potentially 2 years of R&D to develop a new material whenever an existing off-the-shelf one may work. That being said, there's still a lot of room for investing in technology, innovation, R&D around these areas. And, even some of that R&D funding. Now there is a new high temperature product line that exists, and it also provided some of the funding required to do this type of detailed testing. So there's a role to play there as well. So I think now that I'm up on the end of the hour here, I think I may just call it there and hopefully leave some time for questions. But I really thank you again, John, for the opportunity to share a little bit more about what we're working on at Fervo and for helping to kick off your inaugural session here.
Well, thank you, Jack. And I mean, I think we all need to congratulate you and your team for just a fantastic stimulation program and for the vision to take this forward. And so I know we do have a lot of questions. So let's just sort of move through those one at a time. Herman Libet. Herman is asking, the performance of unconventionally drilled and completed fracking wells is limited. Any comments on the economics of such wells, and any comments on his statement in general?
Yeah, I mean, I don't know exactly what you're getting at. I think if you look at, a common metric is new rig oil per month. You see that going up over the last 10 years. So people are getting more efficient in terms of getting more initial production from wells, whether it's through longer laterals or through larger stimulation jobs. You've for sure seen production improving, but it's definitely challenging and basin specific and so forth. So I can't really comment too much more on that question.
The next question, Bert Bland has a question on slide 9, and he's just indicated, I think it's slide 9. He's wondering about your units on pricing. Is it dollars per megawatt hour?
That was, yes, dollars per megawatt hour.
Okay, great.
That's what we were looking at there.
Great. And so Nick Cameron has another question related to comparisons with unconventional oil and gas wells, and the fracs and shale gas oil wells aim to deliver flow from the matrix into the well. It looks like your 3-well scheme relies on flow from the injection well into the frac, plural, and to the producer. How would you avoid short circuiting the flow down a single frac connecting both wells?
Yeah, well, you're exactly right. And I think that's obviously one of probably the biggest difference between unconventional shale wells and these types of horizontal geothermal systems is that, we need pairs of injectors and producers. We need to cross flow between the wells to extract that heat. And I think you're right. It does beg the question of, if some of these fractures are more permeable than others, will short circuiting occur? But that's where I showed that modeling example of where we actually have looked into that. And that's just one example. When you start having hundreds and hundreds of these fractures along your wellbore, that helps to mitigate that challenge. The other thing I would say is, you look at a lot of the studies have in geothermal around short circuiting have focused on natural fracture conductivities. And when you look at a fault, for example, if you look at a typical hydrothermal well that's drilled open hole and is trying to hit natural faults or natural fractures for permeability, typical well will have maybe 1, 2, or at most 3 productive feed zones. And each of those faults are, hugely permeable, providing 1,000 gallons a minute or 2,000 gallons a minute or more in some cases. And so when you look at those types of permeabilities, that thermal short circuiting is for sure a challenge. When you look at conductivity or permeability of fractures that are propped, they're all significantly lower than what you would, not a single one of those fractures is going to deliver you 1,000 gallons a minute, but you take them at, reservoir transmissivity basically is the sum of all the conductivities of every fracture. And so you can meet that overall transmissivity, but have it much more distributed along the wellbore, and the impact of every individual one is less. And the last thing I would say is there will always be some variability in conductivity and the flow properties of the fractures. But if you're pumping if you're getting good flow distribution, which we're seeing we are through the DAS data, while you're pumping a given treatment stage, and you're getting equal amounts of proppant into each zone, you should also tend to mitigate that and have more similar conductivity along the wellbore. But it's for sure a good question.
And another good question from Eileen Zaborowski. And Eileen would like you to sort of expand a little bit more on your last question, and what are some of the diagnostic methods that will tell you your fracture numbers and spacing, and presumably both at the injector and the producer.
Yeah. Well, there's a lot of advances that are happening there. I mean, so one is you start by just designing it through, understanding what's the fracture spacing that meets your requirements. You can run models and simulations like I was showing you to really hone in on what the optimal fracture spacing is. Then you have to ask yourself, when you actually go out and do it, can I achieve this, or am I achieving what I set out to do? And there's a lot of interesting diagnostics that are coming out, and particularly fiber optics based methods, both in-well fiber optic diagnostics as well as cross-well, meaning whether, and the difference is if you have the fiber in the well that you're actually treating at the time, or if you have the fiber in a adjacent offset well that you're not treating at the time. So in-well fiber, I showed you some data from one of our sites. You can use distributed acoustic high frequency measurements to understand which clusters are taking flow. And you see that in real time throughout a given stage. And so that acoustic activity should be proportional to the flow rate going through each cluster. And so you can actually start quantifying, first of all, did each cluster break down, and how good am I at doing at distributing that flow evenly across all clusters within a given stage. And then a great example of crosswell fiber, which I believe at Forge, they're going to have an opportunity to do this. It requires you to have both wells in place prior to doing the stimulation, but you can measure crosswell strain-based fiber optics diagnostics and understand and pinpoint where fractures are propagating and intersecting the offset well. So that's a really exciting and innovative area for more real-time diagnostics.
Herman has another question, and maybe a leading question, Jack. Are these mode 1 tensile fractures in the models, and let's frankly take it in reality?
I think so. Yeah, they absolutely are mode 1. I mean, we were treating above the frac gradient in this case, and so for sure we're creating tensile fractures. I see another question that says, are the models that you showed were sets of planar fractures? Do you have evidence from your projects that the fractures are actually planar? I can't share a whole lot of detailed data on that at this point, but I think broadly speaking, predominantly they are planar from what we're seeing. Is there interactions with natural fractures? I'm sure there is, but does it, how much does it matter to really understand it is another question, one that we're going to continue to look into. But at least at the near wellbore, I model them and also think about them as planar fractures that are propped and provide that near well conductivity to get your flow out into the reservoir. What's happening a little bit further out is obviously a more challenging question to address.
Amanda Kolkar is wondering whether your sensitivity analyses have been published. And if so,
they have not so far been published, but we'll begin publishing a lot more frequently soon, and hopefully we hope to share a lot of the data from these projects at the Stanford workshop in February.
Herman, he's going for the trifecta. This third
Okay.
question. Any comments on the flow rate over time for the models?
Yeah. Flow rate over time in the models is primarily, I mean, in the models, it's fixed constant, but what we do see is changes in the leak off rates over time. We tend to see leak off rates being higher. What I mean by that is subsurface leak off that needs to be made up. We see them higher earlier on, and we see them diminishing over time.
Jack, there's just too many questions for you. I think what I might do is I'll have Gosha transcribe them, and we'll reach out to you independently to answer some of these, because there's about 10 or 15 more questions.
Yeah, I see that. Well, I really appreciate all of the interest and all the questions. I will do my best to try and answer some of these offline. But please feel free also to reach out if you'd like to chat more about this. I'm always happy to chat a little bit more.
So, Jack, I can't thank you enough. I mean, congratulations to you and your team. Thank you so much. I'd also like to thank Gosha Skorin for putting together the webinar. And we'll see you in a month from now, everyone. Thanks for attending.
Thank you, John. Thank you.